Here we'll discuss limits of rational functions, just reminding you that rational functions are polynomials in the numerator divided by a polynomial in the denominator. So it's a polynomial divided by a polynomial. That's what makes a rational function. Now, remember that polynomial functions are smooth, continuous curves without any breaks or asymptotes or holes. Now, rational functions can have holes in the graph. They can also have vertical asymptotes. But other than that, they're mostly smooth curves. They behave like polynomials, except that they have holes and asymptotes. So let's look at this example number 14. We have x squared minus 4 over x minus 2. Now, this is a rational function, and it's possible that at x equals 2, the function is continuous, and we don't need to worry about using any specific technique, but we can only find out if that is the case by plugging in the number first. So when we plug in the number, we get 2 squared minus 2 divided by 2 minus 2. So that's a 0 over 0. 0 over 0 tells us that there is a hole in the graph. And the factor that is causing the 0 in the numerator can be cancelled with the factor that's causing the 0 in the denominator. So in order to be able to cancel the factors, we need to first factor the expression in the numerator. So remember that x squared minus 4 is the same as x squared minus 2 squared divided by x minus 2. Remember that this is a difference of squares. So what is this? X squared minus y squared is a difference of squared. Can be split into or factored as x minus y times x plus y. So the minute you recognize that this is a difference of squares, the way you're going to factor it is by using this standard form. So that is x plus 2 times x minus 2, the whole divided by x minus 2. Remember that x is approaching 2. So if we plug in 2, we get a 0 over 0. But since x is approaching 2 and it's not equal to 2, we are allowed to cancel these two non-zero factors. Now, the minute we cancel the x minus 2, we do not have the 0 over 0 problem. So now we substitute the limit back in and we get 2 plus 2, which is equal to 4. So what did we do? We tried to use the method of substitution first. That did not work. We got a 0 over 0. 0 over 0 tells us there's a hole. We can get rid of the factor that's causing the 0 in the numerator with the factor that's causing the 0 in the denominator. But first we need to factor the expressions. We factored x squared minus 2 squared and wrote it as x plus 2 times x minus 2. And then we found the common factor x minus 2 that got cancelled. Now we were able to cancel x minus 2 because x is only approaching 2. X is not equal to 2. So we can cancel two non-zero quantities, and that's how we canceled the x minus 2. Now once we've cancelled the factor that's causing the 0 over 0, we can plug the number 2 back into the expression and we get 2 plus 2, 4, and that's the limit of our function as x approaches 2. Now, what if we had to find the limit of the same function as x approaches 1? What is the first thing we always try? Substitution. If substitution works, we don't have to go through all this work of factoring. So let's substitute. So we get 1 squared over 4 divided by 1 minus 2. 1 minus 4 is negative 3. 1 minus 2 is negative 1, and that's equal to 3. We did nothing, no factorization, because substituting the limit actually worked. So every time, always try substituting first. Now when we try substituting, here again we get a 0 over 0. 1 minus 1 is 0. Same thing in the denominator, 1 minus 1 is 0. So now obviously we have to do something more, because this tells us there's a hole in the graph. And if there's a hole, we should be able to find limits somehow. So the technique that we use first is factoring. X minus 2 the whole squared is the same as x minus 1 times x minus 1. So x minus 1 the whole squared is x minus 1 times x minus 1. Just like x squared is x times x. Now the denominator can be factored as well. So that's x minus 1 times x plus 1. That's because we can look at this as a difference of squares, x squared minus 1 squared. So once we've factored it, the good thing is that the x minus 1, which was really the factor that was causing the 0 in the numerator and the 0 in the denominator, get cancelled. Now at least we don't have a 0 in the denominator, which means we can plug in 1 minus 1 in the numerator, so that's a 1, divided by 1 plus 1, so that's equal to 0 over 2, which is equal to 0. So we found the limit by cancelling the common factor. Now look at this one. Plug in a 2, you get 2 squared minus 18 plus 14, so that's equal to 0. In the denominator we have 2 minus 2, which is equal to 0. So 0, 0, 0 over 0 tells us there's a hole in the graph. If there is a hole, we should be able to find the limit by factoring and then cancelling, just like the previous problem. So when we factor the expression, we'd have to find factors of 14. 14 ones of 14, but then the factors have to add up to negative 9. So 14 is also equal to 7 times 2. 7 plus 2 is plus 9, but what we need is negative 9. So we can think of this as minus 7 times minus 2. So that is the right pair, because when we add the 2, we get minus 9. So we use that and get x squared minus 7x minus 2x plus 14 over x minus 2. Factor the expression in the numerator and of course keep writing limit as x approaches 2. Limit as x approaches 2. The common factor between these two is x, so that's x minus 7. Common factor between these two can be taken as negative 2. That would give us x minus 7. Remember, these two have to match. It's x minus 2. The common factor is x minus 7, so factor that out. And you get x minus 7 times x minus 2. Remember that. And that remain. That's how we get the x minus 2 divided by x minus 2 limit as x approaches 2. Now, this was the whole point of the factoring. We wanted to get rid of the factor that's causing the 0 in the numerator and the 0 in the denominator. Now we are ready to plug in x equals 2 and try again. So that's 2 minus 7, which is equal to negative 5. And that's the limit of the given rational function.